evening, Saintsmen. I'm doing instruction for lesson 8.4. My apologies on the late posting of this, but just want to make sure that you guys got a copy of this instruction so you could get right to work with the next assignment. May need to take a break during this instructional video to cough. My apologies, I know it's a little awkward, but as this video is being made, so you guys know I've had to be out because I've been a little bit under the weather. So here we go. Let's get this diagram set up. Oh goodness, the pen is in bad shape. Oh wow, what happened here? Okay, guess that's all going away. Maybe try to do that again. All right, well, I went to go pick this up today from school and my pen has been damaged. So let's try this all one more time. Good grief. I cannot believe this, guys. That is not good. I am not happy about that. Okay, we have this triangle right here. ABC is the triangle. What we're going to have here is the following instance. It's going to be a specific instance of triangle, and it's going to happen in diagrams as we're moving forward into your quiz, which is going to be on the next lesson right after 8.4, after this lesson, right? So, so we have this. If we have ABC with line DE, right? And we have DE as a line drawn interior to this triangle, and it's parallel. So if BC and DE are parallel, then the result is the following. There's going to be a proportionality that's going to happen. Remember, I have two triangles here, right? Triangle ADE and triangle ABC. And we already know, and we can already surmise rather quickly, that these two triangles are going to be similar. It should be straightforward. And here's why. Gentlemen, look, we have two sets of parallel lines, which is going to create two sets of corresponding angles. Moreover, we're going to have this angle A, which is reflexive into itself. We're going to have angle-angle similarity. This goes back to lesson 8.2. All right. So we have angle-angle similarity. Now, because of that, we have these other little sub-segments right here, DB and AC, and they have a relationship. Their result, and the way we can come through this, by the way, is through angle addition, and it's not a theorem that I'm going to go through, because again, this is, as I said before, the juice isn't really worth the squeeze on this one. But we know that AC and AE are going to be proportional in the ways that AD and AB are proportional as well, right? So then these little sub-segments, right, their angle addition, EC and DB, are also going to have a similarity. Now, the converse is also going to be true. Meaning the following, that if I were to have this triangle here, and I were not given this parallel marking, but I were given dimensions that would create proportionality between EC to AE as DB is to AD, then I have similar triangles, right? Because effectively I'd have an angle-angle relationship. So let's employ this right away, because once we see this in use, it will make a lot more sense. You know, sometimes these things are a little bit more difficult when we're just speaking in the theoretical. So we have that instance. I've just reoriented the triangle. There's been a little rotation here. V, W, X, Y, and Z. So Here we go. We have 10. We have 8. We have 12. And we need to solve for the VW. This is going to be pretty straightforward, right? Because it's going to be the segments, right? This guy, VW, to the other leg, right? Working from V to VZ. So VW to VZ will be the same as the bottom segments, WX, working to ZY. All right? So, we can actually do our cross product from here, right? In order to solve this. Now, other ways to set this up. Is it the same to say that, for example, if I were going to go WV, hold on a second, I got to snooze an alarm real quick. Excuse me. If I were to take VW to the leg, right? So VW to WZ, or to WX, is VZ to ZY. Will that be the same? And I think you guys very quickly see that, yeah, those are going to have the same identical cross products, right? So nonetheless, let's actually just plug in the numbers. VW, which we don't know. VZ, which is 10. WX, which is 12. ZY, which is 8. Taking my cross product. So I'll have 8 times the quantity VW is equal to 120. Divide both sides by 8, and VW is equal to 15. And I'm done. Next example. A little bit more exotic of a diagram here. So I'm going to have 2 lines just kind of out here in space. We won't draw their intersection, but they, eventually will, of course, like all lines do that are not parallel. I have 3 lines that are going to go and cross these lines. I have a number of intersections. So let's go ahead and name these intersections A, B, C. Goodness, guys, I apologize. I don't apologize for the quality of my pen. That's really tragic and unfortunate that has been damaged so much in my absence of 2 days. The spare pen tips that I have are all at school when I'm broadcasting from home. So I have these guys, and let's see here. Let's show all the things that we know in blue, given in the diagram. This guy is 35. DE. AB is 30. BC is 12. And I have congruence. This angle, and this angle. So, we are going to solve for DF. Now, what do we know? First and foremost, it's not marked, but we can tell that AD is parallel to BE, which is also parallel to CF. Now, how can I tell that in this diagram right here? Well, it's through this. What is the angle relationship with these angles that are congruent? These are corresponding angles. So that we have corresponding angles that are congruent means that we have these parallel lines. So these are corresponding angles. Now, there isn't the intersection, but it could happen. It will happen, right? So it's going to create effectively that same proportional relationship. So AB to BC, because of that parallel nature, is going to be proportional of DE, right? So top to bottom will be proportional to top to bottom, right? DE to EF. So in order to solve for DF, we're going to have to solve for EF first. So let's go ahead and create that proportion. So we'll have 30 to 12 is equal to 35 to EF. Take a cross product, right? So 30 times EF is equal to 12 times 35, which is 420. We'll divide by 30 on both sides, and we'll get that EF is equal to 14. We know through segment addition that DE plus EF will get us that sum of DF, which is what we're looking for. We know that DE, back in the diagram, right, up top, was equal to 35. EF we just solved for, which is 14. We find the sum of those two. We know that DF is equal to 49. All right, I've got one more theorem for you, and then just one more example. It's going to be a quick night, all right? Quick little exercise for you guys. So next is what's known as the triangle. Oops. The triangle bisector theorem. So here we go. We have triangle ABC with CD being an angle bisector, okay? So this is what our theorem says. If CD is an angle bisector, then we're going to have a proportionality relationship here. That's going to be a result, right? That AD, right, one of the bisected segments, to the other bisected segment, DB, these guys are going to be proportional to each other because they're not going to be congruent, right? The angles that are bisector, remember, the angle bisector in a triangle is only the same in an isosceles triangle, right, where it's going to create the same as the median. The median is where we actually have these segments are going to be congruent. So this isn't necessarily so, right? But they will be proportional to the legs that are created too, right? So AC, the legs that are going to be the other parts of these triangles, AC to BC. Think about why this is so. You have to think side angle side, right? So here we go. Let's actually employ this thing. Triangle bisector theorem. New little diagram. It's this. A, B, C, D. $18, Y, 63, 42. And we're going to solve for y. Now, think about what we just did before. It's this triangle bisector theorem, right? So what it's saying is that these segments that are creating that bisector, right, that are created by the triangle bisector are going to be proportional. AB, I'm sorry, let's actually work for the bisected portions. BC to CD, right, is going to work with the legs that are created off of them, right? The leg off of BC, right, which was 18, that leg is going to be AB, 42. And then on the other side, right, it's going to be 63, which is AD. So then actually let's input some segments here, okay? or input some values. So we'll have 40, oops, BC is 18, CD is Y, AB is 42, 263. I could take a cross product, guys, but I'm a little bit lazy. I don't like to work with numbers that are so exceptionally large, right? Just do a little reduction here. Actually, no. You know what? You guys need to use calculators. Let's actually do this here. All right, punch it into a calculator. So the cross product, 18 times 63. Punch it into a calculator, you're gonna get 1134, which is gonna be equal to 42y. You're gonna divide both sides by 42. And your y is going to be 27. Now, you know what I was trying to do is I was actually going to reduce this thing over here and go 18 to y, divide both of these and reduce it to, both are divisible by 21. So it'll just be 2 to 3. Then take a cross product, right? So then I'd have 54 is going to be equal to 2y, which of course is going to still be 27. So just supporting instruction in that other way. You guys can see this is a really short lesson. It's a pretty straightforward little chapter. We will have our test in just a couple of days. Stay tuned for the practice test instructions. Good luck.